Hello and welcome to week 7 in database systems. Our agenda for today is to go over the assignments and then talk about chapters 23 and 24. First, the assignments. Chapter 23 centers on distributed database concepts, and chapter 24 talks about NoSQL databases and big data storage systems. For your first discussion, you're to talk about chapter 23, which is the distributed databases. That is due by the end of the week. And then discussion 2 is to talk about chapter 24, NoSQL databases, and then do recall that by the end of week 8, your course project phase 3 is due for 200 points. Moving into week 7's objectives, we're going to talk about chapter 23, which deals with distributed database concepts, distribution transparency, fragmentation transparency, replication transparency, design issues related to horizontal and vertical fragmentation, concurrency controls and recovery techniques, query processing, and then categorization of distributed database management systems. Chapter 24 is going to center on NoSQL systems in general, big data in particular. General categories include things such as document databases, key value stores, column-oriented databases, graph databases, and some systems that use techniques spanning two or more of these categories. Also, we'll talk about consistency paradigms and the CAP theorem. Week 7's discussion, first discussion centers on chapter 23. You're asked, what are the main reasons for the potential advantages of distributed databases? Do respond to that prompt in 250 to 300 words, making sure that you restate the prompt using your own words rather than repeating the question back to the class because they kind of know the question. Make sure that you do respond to at least 2 of your classmates in a constructive way, building upon what they have to say. Week 7's discussion number 2 centers on chapter 24. You're asked, what are the main characteristics of NoSQL databases in the area related to data models and query languages? Or you can respond to, what are the main characteristics of NoSQL systems in the area related to distributed systems and distributed databases? Pick one of those 2 questions and answer them with your initial contribution. After that, do ensure that you respond back to 2 of your classmates' post, adding to what they have to say in a constructive way. Do make sure that you respond to the initial prompt with at least 250 to 300 words, including a citation that supports any claims that you may make. The course project phase 3 is also going to be due soon at the end of week 8. The summary is to apply all the acquired knowledge in the last project assignments to create a database schema. For this project, the ERD is provided to you. So instead of creating one, you're going to be given one. Your deliverables are a set of the following. SQL scripts with your name as follows: your last name, first name, followed by project, and then phase 3 SQL. An MS Word document that contains the output, also formatted with a similar naming convention, and a zip file that includes the 2 above mentioned files, or you can submit them as 2 distinct submissions. You do need to use MySQL database management system from Oracle, and you want to use the community version of that. In addition, the workbench that accompanies it. You want to follow steps 1 through 3 of your course project phase 1 to install the required software components. The following is the schema that you're given, ERD diagram, from which you need to convert that into a schema. Be alert and look for the specifics, including entities, attributes, and primary keys and the relationships between those. You need to be very clear about this so that you can do so appropriately, model them appropriately inside of MySQL. The second step in the project is to create a new database from MySQL and produce the required SQL file and then drop the table. So create a database as you did in the course project phase 1 deliverable, and you already created a database using MySQL DBMS system. Refer the attached video, course project phase 1 video.mp4, for a demonstration of how to create a new database using MySQL. This video was initially presented to you for phase 2 of your project. Also reference the supplemental text available for free download as part of your University of Cumberland's library. The MySQL Database Usage and Administration Manual, copyright 2010, and the link is provided to you. Utilize the SQL dialect you learned so far in the course for MySQL. Use the file supplemental textbook as needed to fill out anything you don't know. Create your script and save it off, naming it as is specified in the assignment. The phase 3, the last step of the lab the third step is to create the following commands at the beginning of your script. Drop table if exist for all the tables that are going to be created as well, and then setting foreign key checks on and off as appropriate. So the first one turns off your foreign key checks and then lets you drop the tables, and then you can turn them back on. Step 4 is to create the tables in your database. Create a new table for each of the entities provided to you in the ER diagram. In step 1, add columns to represent each of the attributes addressed in the ER diagram as well. Design a primary key as noted in the ERD diagram. Designate the foreign keys also in the ER diagram. Enable referential integrity on the relationships as needed, and enable cascading updates as needed on the relationships. Step 5 is to designate the data types. Update the data types as needed to enforce the domain constraints of the data. This needs to be completed for every column for all tables. Dates, they should have a date data type as designated type. Surrogate keys shall be all auto numbered, and the character types should have a character data type designation. Step 6 is to add column constraint designation. Grade designation must be one of the following values. So you can't have, actually you should not have, okay. E and W is enrolled and withdrawn. Students' first and last names are not to be designated as null. So you cannot have a null first name or last name. Course credit hours shall be between 1 and 4. Instructor first and last name must not be null, and course name designation has to be unique and cannot be null. Step 7 is to add some data to the tables. Use the insert operator to add a minimum of 2 to 3 rows of data per table in the database. You're free to use any values you might feel are appropriate. Remember, you're required to add data to the parent table prior to adding into the child tables so that referential integrity can be enabled. Execute the script. Your script must incorporate a commit statement at the end to ensure that the transactions goes through. Incorporate the show table command that shows the tables that you created. At the end of the script, must include those insert or select statements to show the values that have been inserted into the tables, and then you execute the script. Copy and paste the output into a Word document, and then upload your work as part of your submission. The tables created, this is the rubric that will be used to grade it. You've created the tables in the ER diagram, that's 20 points. The columns have been added, another 20 points. Primary keys, again, 20 points. Data types, and that's another 20. And then 40 for the relationships created, appropriate to the ER diagram for 40 points. And then data was added, that's also 40 points. And then the final is the column constraints, a final 40 points, bringing you to your total. Chapter 23 centers on distributed database concepts. An introduction. Distributed computing systems in general consist of multiple processing units scattered across something that are interconnected by some form of a network. The degree of distribution depends upon the particular instance. Generally speaking, though, they're fairly close to each other. Nodes cooperate to perform certain tasks, so they're working together to do something in common, and there's typically partitions of large tasks are spread across multiple of these units so that you can solve the problem in a more efficient way. Big data technologies are similar in a way because they do combine distributed and database technologies, but they also deal with vast amounts of data that also may be of varying types and also of varying quality, and typically is moving very quickly. Our first discussion of distributed database concepts. So what constitutes a distributed database? It's a connection of database nodes over a network of some sort, so they're not centrally located on a single computer. There's a logical interrelation of the connected databases, so they have something to do with each other. They're not just standalone and happen to be on the same network. And there's possibly absent of homogeneity among the connected nodes. And what that basically means is those nodes may be differing in what they look like. They may not all be the same exact type of computer, may not even be the same necessarily database management system or distributed database management system. And a distributed database management system is a piece of software that manages distributed databases. A local area network is a means of connecting computers together. It's typically associated with switches and hubs, and there are cables that are involved, typically speaking, that are connecting sites together. Long haul or wide area networks include things like satellite connections, wireless networks, potentially, fiber optics, and various other types of connectivity. Network topology defines the communication path, so how things are hooked together. And transparency is about related to hiding the implementation details from the end user. There are various types of transparency. They include things like data organization, so the location transparency and naming transparency. Basically, this means that you don't necessarily need to know where something is stored in order to use it. Replication transparency is you don't really care how things are kept in sync and how data gets from one place to another. Fragmentation being that data may be split or sharded in various ways, and you don't particularly care if it's vertical or horizontal as long as the queries that you submit return with appropriate values. The design is also something you don't necessarily care too much about, nor do you care about how the things are actually executing. Those things should all work without you necessarily knowing how it's being done. So it's essentially abstracted from consideration. Here's an example of a distributed database diagram. And the primary distinction here is that it's potentially including a geographic location connected together by some form of a network. Availability and reliability is very important within a database, a distributed database, as any type of database. Availability speaks to the probability that the system is continuously available during a certain window. Reliability is that the probability that the system is running and not down at a certain point in time. Both directly relate to faults, errors, and failures. Fault tolerance is an approach where one attempts to mitigate and manage these sort of conditions through either software design or hardware. Horizontal scalability deals with expanding the number of nodes in a distributed system to include or to increase the capacity essentially of the system, whereas vertical scaling is about expanding the capability of a given node or instance inside of that cluster. Partition tolerance deals with the fact that the system should be able to continue operating while the network is potentially partitioned, meaning that there may be some link within the network that is not necessarily available at a given point. When it becomes available, things should return to a good state. So the system shouldn't go down if one partition, one link essentially within the network goes down. Autonomy determine the extent to which an individual node can operate by itself. Design autonomy deals with the independence of data modeled using and transaction management techniques among the various nodes. Communication autonomy determines the extent to which each node can decide on sharing information with other nodes. Execution is about how much an individual node can, the independence of users to act as they please. So who can do what? Advantages of distributed databases include things like improved ease and flexibility of application development, development at geographically dispersed sites, increased availability, isolate faults to their site of origin, improve performance through the use of data localization. Basically, that just means that the data is where it is going to be used. Easier expansion via scalability. So it's easier to increase the capacity of a distributed database because you're adding additional nodes to the processing and storage capabilities versus having to go and potentially buy larger hardware. Section 23.2 deals with data fragmentation, replication, allocation techniques for distributed database design. Fragments are basically logical units of data that may be sharded or separated out into small pieces. Horizontal fragmentation is called sharding. That's where a horizontal fragment or shard of a replication is a subset of the tuples in a given relation. It can be specified by a condition of or one or more attributes or by some other method. This is deciding how you're distributing those shards. Groups of rows to create sets of tuples. Each subset of has a certain logical meaning. Vertical fragmentation is about defining a relation vertically by columns. It's by putting columns in certain locations based upon need. Keeps only certain attributes of the relation. Complete horizontal fragmentation, you essentially are applying a union operation to the fragments to reconstruct at a given location. Complete vertical fragmentation is to apply an outer union or full outer join operation to reconstruct the relation. You typically don't see as much vertical fragmentation as you do horizontal. Sharding is very commonly used. Vertical fragmentation, not quite so much. There are also mixed or hybrid fragmentation approaches. This is a combination of horizontal and vertical fragmentations. A fragmentation schema defines a set of fragments that include all the attributes and tuples in the database. Allocation schema describes the allocation of fragments to nodes of the database management system or the distributed database system. Full replication of distributed databases, that's where replication of the whole database at every site in a distributed system. This improves availability remarkably, but it also updates operations can be very slow because they have to be updated across the entire system. Non-redundant allocation with no replication, or maybe it's some a certain amount of replication. Each fragment is stored at exactly one site, and there are also this concept of partition replication, where some of the fragments are replicated and others are not. This is defined by a replication scheme. And the data allocation, which is data distribution, each fragment assigned to a particular site in the distributed system. Choice depends on the performance and availability goals of the system. There's also this concept of potentially having enough data replicated so that you can reconstruct it if one of those nodes were to fail. So perhaps you have 3 copies of the same data located in various locations, and you keep track of where those are at so that if for some reason 1 or 2 of the systems go down, you still have not lost the data. Examples of fragmentation, allocation, and replication. A company has 3 computer sites, 1 for each department. Expect frequency access by employees working in the department and project controlled by that department. This is in figure 23.2 and 23.3 for examples of fragmentation among the 3 sites. The 23.3 talks about the overview of concurrency controls and recovery in distributed databases. Problems specific to distributed database management systems include multiple copies of data items, failure of individual sites, failure of communication links, distributed commits, and distributed deadlock. So a particular copy of each data item designated as a distinguished copy. You basically locks are associated with the distinguished copy, primary site technique. All distinguished copies are kept at the same location. Kind of a little risky because it's kind of all of your eggs in one basket, if you will, so probably not a great idea. Primary site with backup, locking information maintained at both sites. Primary copy method distributes the load of lock coordination among various sites. Voting methods as a way of doing concurrency control. There's no distinguished copy. Lock requests are sent to all sites to contain a copy. Each copy maintains its own lock. If the transaction that requests a lock is granted that lock by a majority of the copies, it holds the lock on all copies. Generally speaking, there's a timeout, and there's always a timeouts of some sort with distributed systems. The results in higher message traffic among sites because you have to do all this voting and communicating back and forth. Distributed recovery. Difficult to determine whether a site is down without exchanging numerous messages with other sites. Distributed commit. When a transaction is updating data at several sites, it cannot commit until certain its effects on every site cannot be lost. Two-phase commit protocol often used to ensure correctness. In the past, that was certainly true of centralized locations. We've now moved to something called eventual consistency, which we'll probably be discussing shortly, but the idea that eventually things come into compliance or into consistency. 23.4 is an overview of transaction management and distributed databases. Sometimes you have a global transaction manager. It supports distributed transactions. The role is temporarily assumed by a site at which the transaction originated. It coordinates execution with the transaction managers at multiple sites, passes database operations and associated information to the concurrency controller. Controller is responsible for acquisition and releasing of all the locks. The commit protocols, there's a two-phase commit. Coordinator maintains information needed for recovery. In addition to local recovery managers, there's a three-phase commit where it divides the second commit phase into two subphases. Prepare to commit phase, and it communicates the results of the voting phase, and then a commit subphase, which is the same as the two-phase commit counterpart. 23.5 is query processing and optimization in distributed databases. The stages of a distributed database query is query mapping, refers to global conceptual schema. Localization maps to the distributed query to separate queries on individual fragments. Global query management strategy selected from the list of candidates. Local query optimization common to all sites in the database, distributed database. Query processing and optimization in distributed databases continued. Data transfer cost of distributed query processing, cost of transferring intermediate and final result files across the network. Optimization criteria is the reducing amount of data transferred. Distributed query processing using semi-join reduces the number of tuples in a relation before transferring it to another site, sending the join columns of one relation R to one site where the other relation S is located, and then join the attributes and result attributes shipped back to the original site. This is an efficient solution with minimal data transfer. Query and update decomposition. Users can specify a query as if the DBMS were centralized. If full distribution, fragmentation and replication transparency are supported. A query decomposition module breaks up a query into subqueries that can be executed at the individual sites. Strategy for combining the results must be generated, and catalog stores attribute list and/or guard conditions to make it all possible. Factors that influence the type of distributed database management system is the degree of homogeneity of the database management systems or the distributed database systems. Your two choices are totally homogeneous, and then there's heterogeneous where they're made up of different sorts of things. The degree of local autonomy, there's either no local autonomy or multiple databases. Multi-database system has full local autonomy. Federated database systems, global view or schema of a federated data of databases is shared by the application. Classification of the various types of databases shows that it's 3 dimensions, distribution, autonomy, and heterogeneity across and putting things into that 3-dimensional space. The types of distributed database systems, there's federated database management systems that they have the following issues. There's differences in data models, there's differences in constraints, and there's differences in query languages. Semantic heterogeneity is there's differences in meanings, interpretation, and intended uses of the same or related data. Design autonomy allows different definition of the following parameters: the universe of discourse from which the data is drawn, representation and naming, understanding, meaning, and subjectivity, subjective interpretation of data, transaction and policy constraints, and then derivations of summaries. Communication autonomy is to decide whether to communicate with another component, distributed system, database system. Execution autonomy, execute local operations without interference from external operations by other components of the system. Ability to decide on the order of execution. Association autonomy, decide whether and how much to share its functions and resources. 23.7 talks about distributed database architectures. There's parallel versus distributed architecture. The types are also of multi-processor system architectures. So a parallel architecture would basically be things happening together, but typically speaking on the same computer. Distributed, you're running on different computers, different processors at exactly the same time. A distributed system is inherently parallel in nature, but a parallel system need not necessarily be distributed. Types of multiprocessor system architectures, there's shared memory, which is tightly coupled. A shared disk, a little less tightly coupled, but using a disk still that is common to everything to communicate, or a disk-like system. And then shared nothing, where there's no coordination between them at all. Database system architectures, the figure A is showing a shared nothing architecture. That has become very common. Figure B is a network architecture with a centralized database at one of the sites, and a fully distributed database architecture is figure C. Generally speaking, things are going to be a shared nothing, or possibly a truly distributed system, which you see in C, or a variation where it looks like it's a shared system. So it looks like it looks like B, but it's not really B, because it's logically distributed, or physically distributed, but logically appears to be not distributed. The general architecture of a pure distributed database system includes things like a global query compiler. It references global conceptual schema from the global system catalog to verify and impose definition constraints, or define constraints. A global query optimizer generates optimized local queries from global queries. And then you have a global transaction manager, which coordinates the execution across multiple sites with the local transaction managers. Figure 23.8 is a schema architecture of a distributed database. You can see here the users with their external view, the global conceptual schema, the local conceptual schemas depending upon where they're at, and the local internal schema, and then the stored data at site 1 through N. A federated database schema architecture is in figure 23.9. It shows an external schema with some federated schemas, and then an export schema, and a component schema, and a local schema for each of the component databases. An overview of a 3-tier client-server architecture. This is a common architecture, not necessarily related exclusively to databases, but the idea here is a division of a distributed database management system. Functionality among 3 tiers can vary. So you have a client, which is interacting with an application server of some sort, typically over some sort of HTTP or HTTPS protocol. And then you have the application server connecting to a database server, typically using ODBC, JDBC, or some other variant of that sort of connectivity. There's an extension to this where basically the application server becomes a web service instead, and you interact from the client, which may be a browser directly using JavaScript to access a web API to perform interactions that is then backed by a database. So a very similar architecture. 23.8 is around distributed catalog management. Sometimes you have centralized catalogs. That's where the entire catalog is stored at a single site. This is the easiest to implement. You have fully replicated catalogs. That's where identical copies of the complete catalog are present at each site. It's faster reads, but you're trading off keeping those things in sync and keeping multiple copies of the same thing. And then you have partially replicated catalogs where each site maintains a complete catalog and information on what is locally stored at that site. In the summary of 23.9, section 23.9, we talked about distributed database concepts. We talked about the concepts of transparency, design issues with horizontal and vertical fragmentation, concurrency control and recovery techniques, query processing, and categorization of distributed database management systems along the 3 dimensions. Chapter 24 centers on NoSQL database technologies and big data storage systems. As an introduction, there is NoSQL. Some argue that it stands for not only SQL. The problem with it is typically it's not named that way. It's typically capital N, lowercase o. So it originated from organizations that did not want to have the restrictions of a highly structured schema and schema on design, not schema on read. As such, they came up with an approach to disparage SQL. The problem was over time they started finding that SQL support was important to their business models, so they included SQL support, so hence the name became very problematic. Some attempts were made to rebrand it essentially as what you see on the screen with not only SQL. That's founded in fiction, not fact. The reality is systems that traditionally were NoSQL oriented are now supporting SQL, and SQL systems also have included many of the capabilities and capacities and characteristics of NoSQL database systems, so the line has become very blurred. The basic idea, though, is that it's focused on semi-structured or unstructured data with a high performance, generally speaking, through some form of distribution around availability and data replication and scalability. Continuing the introduction of NoSQL systems, they focus typically on things related to big data. The typical types of applications that use NoSQL include things like social media, web links, user profiles, marketing and sales, posts and tweets, roadmaps, and spatial data, and so on. Oftentimes, some of these things that traditionally would have been put into a NoSQL database are actually instead now being stored in things like a data lake, where it's essentially a large storage system, and then various sorts of technologies are involved in accessing it from that medium. Moving into 24.1, which is the introduction of NoSQL systems. Bigtable was kind of one of the first ones to start this. It was Google's proprietary NoSQL system. It was very much of a column-oriented or wide column store. Did very well for accessing things with lots of columns. DynamoDB was a key value, or is a key value data store. Cassandra was created by Facebook. It used the concepts of both key value and column-based approaches. MongoDB and CouchDB are both document stores. Neo4j and GraphBase are types of a graph database, and that's a mathematical graph of nodes and edges stored in a way so that you can do interesting analytics on it. OrientDB combines several of these concepts, and then there's database system classified on the object model approach, or there's some that are native XML or JSON type approaches. NoSQL characteristics related to distributed databases and distributed systems include things like scalability, availability, replication, eventual consistency, replication models, master-slave, master-master, sharding of files across the clusters, and high-performance data access. Many of these things, including eventual consistency, have made their way into both traditional relational database systems and also a new breed of things called NewSQL, which are a mixture of the best of NoSQL technologies with traditional relational data stores. NoSQL characteristics related to data models and query languages. Schemas are not necessarily required, although there is sort of a implicit one that you must know in order to use the data. The data is evaluated, or a schema, if it exists, is evaluated on read, not on create or write. Generally speaking, the query languages aren't quite as robust. Performance could be problematic depending upon what's going on, but typically speaking, NoSQL and big data systems in general are utilized because traditional relational database systems aren't going to work. There is typically some form of versioning and support for things such as a schema evolution, where what a schema is changes over time. There are various categories of NoSQL systems. We've talked about them briefly. There are document-based or document-oriented NoSQL systems, NoSQL key value stores, which is basically a name value pair that's stored, column-based or wide column NoSQL database systems, graph-based systems, hybrid NoSQL systems, object database systems, and XML databases. The various levels of consistency among replicated data items, enforcing serializability, the strongest form of consistency. There's high overhead, however, it can be reduced through read-write performance, operation performance. The CAP theorem states that basically you have a trade-off between consistency, availability, and partition tolerance. You may be able to give up one of those for a short period of time. Not possible to guarantee all three simultaneously. Generally speaking, though, it's a trade-off, and it's kind of an interesting theory because you don't really have control over some of those. Partition tolerance basically means a link inside of the network goes down, so there's an isolated element of a distributed system. That can only work for so long. When it comes back online, the idea is that you end up being consistent eventually, or you stop working. And the idea here is that it's about distributed systems without necessarily doing data replication. Designers can choose two of the three to guarantee weaker consistency level is often acceptable in NoSQL distributed systems. And that's what I just said. CAP theorem implies that basically you can pick two out of the three, but you don't necessarily get to truly pick two of the three. Some of them are required. You need to be able to handle partitioning. You don't have a choice. So, and you need to have things available. So, I mean, it's an interesting argument, but it's got to be viewed from a temporal perspective. Guaranteeing availability and partition tolerance is more important. To facilitate this, eventual consistency is often adopted. Document stores are a collection of similar databases or documents. Individual documents resemble complex objects or XML documents. Documents are self-describing and can have different data elements. The basic idea is that a document is whatever the application that reads it and writes it needs in order to do its thing. They typically are very much the opposite end of the spectrum of a column-oriented database, where it's a particular row is essentially a document. Documents can be specified in various formats. They include things like JSON, XML, Parquet, various other types of formats. MongoDB is one of the more common ones. It certainly was one of the early ones. It supports a variation of JSON called BISON, which is a binary form of JSON for performance reasons. Individual documents are stored in a collection, and an example command is first parameter specifies the name of the collection. The collection option includes the limits on size and number of documents. So you have db.create collections, something called project, and it's capped at true. The size is some number, and the max is 500. Each document is a collection that has a unique object ID called ID. A collection does not have a schema. The structure of the data fields in the document chosen based upon how the documents will be accessed. So the reader of the document determines the schema, not something that's native to it itself. Users can normalize or denormalize the design. Document creation is based by using an insert command. You insert a document into the collection. Document deletion is used using the remove operation to remove the document from the collection. So in that regard, you can think of a collection of being similar to a table, and a document being something similar to a row in a table from a relational perspective. It's a little more complex than that because they don't necessarily have to be the same structure or schema, but it's that kind of concept. Figure 24.1 is an example of a simple document in MongoDB. And you can see it's, in this case, it's basically a JSON document that's showing you the ID is P1 for both items, and the other is variations on how things are being stored inside of the document array. 24.1 is an example of a simple document as well. This is more normalized in C, and D is inserting the documents into the collection. MongoDB distributed systems characteristics. It typically uses something like a two-phase commit used to ensure atomic and consistent multi-document transactions. The idea is that a document unto itself is inherently transactional, right? So it is atomic by itself. But what if you have two documents that go together? That's where you have to do something like a two-phase commit. Replication in MongoDB is the concept of a replica set to create multiple copies of different nodes. It's a variation on the master-slave approach, primary copy, secondary copy, and arbiter. Arbiter participates in elections to select a new primary if needed. Replication in MongoDB, all write operations applied to the primary copy and propagated to the secondaries. Users can choose to read, read performance. Read requests can be processed at any replica. Sharding in MongoDB is horizontal partitioning, divides the documents into disjoint partitions or shards. This allows adding more nodes as needed. Shards are stored on different nodes to achieve load balancing. Important to understand, though, that when you're doing sharding, you're doing so based upon some field. That means that you need to consider that field very carefully so that you can then find which shard something belongs on based upon it later on. It also means that if you want to be able to enable multiple shards and increase them over time, you have to consider that in your key selection as well. Partition field, that's the shard key, which is what I just talked about, must exist in every document in the collection, and it must have an index. Range partitioning is whenever you use chunks based upon a range of key values. This works best in range queries. Hash partitioning is partitioning based on the hash value of each shard key. When we talk about no SQL key value stores, a key value store focuses on high performance availability and scalability, can store structured, unstructured, or semi-structured data. A key is a unique identifier that's associated with a data item used for fast retrieval. The data item itself can be a string or an array of bytes. The application that's reading that array of bytes or string does the interpretation of the structure. There is no query language. DynamoDB is a part of Amazon's Web Services SDK platform. It's a proprietary database approach. The table holds a collection of self-describing items. The item consists of attribute value pairs. Attribute values can be a single or multi-valued. Primary keys can be used to locate items within a table, and they can be singular attributes or a pair of attributes. Volademort is an open source key value system similar to DynamoDB. This is something that's kind of faded from use. You're not going to find this out there in use very often. It's a simple basic put, get, and delete, has a high level of formatted data values or high level formatted data values, consistency hashing for distributed pairs, consistency and versioning, concurrent writes are allowed, and each write associated with a vector clock. Figure 2.4 or 24.2 is an example of a consistent hashing approach. The basic idea is that you should always get a reasonable distribution of your hash function so that your load is reasonably evenly distributed across your stores. Examples of other key value stores: Oracle has a key value store, Oracle NoSQL database. Redis key value stores is basically a cache and store. It caches data in main memory to improve performance, offers master-slave replication and high availability, offers persistence by backing up the cache to disk. This is utilized a lot in web applications, and the idea being that you retrieve something from a cache so that it's much faster. Apache Cassandra, this is still around, still used, offers features from several NoSQL categories. It's used by Facebook and many others. 24.5 is around column-based or wide column NoSQL systems. Bigtable was kind of the first one and kind of kicked off this whole approach. It's a distributed storage system for big data. It's used in Gmail, Google File System for data storage and uses Google File System for data storage and distribution. Apache HBase is a similar open source system, uses HDFS for the data storage, which is the open source implementation of something very similar to DFS or GFS. It can be used in Amazon's S3, lots of other places as well. The HBase data model and versioning, there's data organizational concepts. You have a namespace, a table, column families, column qualifiers, columns, rows, and then data cells. The data itself is self-describing. HBase stores multiple versions of data items. There's a timestamp associated with each version. Each row in a table has a unique row key. The table associated with one or more column families. Column qualifiers can be dynamically specified as new table rows are created and inserted. Namespace is a collection of tables. Cells hold the basic data items. This is an example from HBase. Notice that we're creating an employee that has name, address, and details. We're inserting name, row 1, and we're saying what its name is. It's first name, last name, nickname, job details, and engineer, and so on. And then some basic CRUD operations, create, table, column, store, and so on, or column family, and then so on, and then put some data in with a put command where you insert, you scan for something, and then you retrieve something. HBase CRUD operations provides only low-level CRUD operations, create, read, update, and delete. Application programs implement more complex operations. It creates a new table and specifies one or more column families associated with the table. Put inserts new data or a new version of the data into an existing data item. Get retrieves data associated with a single row, and scan retrieves all the rows. Each HBase table is divided into several regions. Each region holds a single range of the row keys in the table. Row keys must be lexicographically ordered. Each region has several stores. Column families are assigned to stores. Regions assigned to region servers for storage, and master slave responsible for monitoring the region servers. HBase uses Apache Zookeeper and HDFS. Graph databases store data as a representation of nodes and arcs. You have nodes, which are vertices, and edges, which connect those nodes. It's possible to store data associated with both individual nodes and with individual edges. That's kind of one of the compelling arguments of a graph database, is that you can have as many attributes on your edges as you have on your nodes, if not more so. Neo4j is an open source system. It uses the concept of nodes and relationships. Nodes can have labels. They're 0 or more. Both nodes and relationships can have properties. Each relationship has a start, end, and end node, and a relationship type. That means that they are directed arcs, so you need to have two of them if it's a bidirectional relationship. Properties specified using a map pattern, and it's somewhat similar to ER or EER concepts. Creating a node in Neo4j, use a create command. It's part of a high-level declarative query language called Cypher. Node labels, and there's also variations of this. There's also Gremlin, which is not necessarily for Neo4j, but it's the same sort of concept. Node labels can be specified when the node is created. Properties are enclosed in curly brackets. Here's an example of creating some nodes and some relationships. This is the example of it creating some relationships between the nodes that were created on the previous slide. Note that there's an attribute on some of these, like hours, which is a property of the works on relationship. A path is a way of traversing part of the graph. It's typically used as part of a query to specify some pattern. Schema is optional in Neo4j, and indexing and node identifiers users can create for the collection of nodes that have a particular label. One or more properties can be indexed. It's important to note too that Neo4j is basically unlimited in size in a big data sort of world. You can have any number of nodes and edges. The Cypher query language of Neo4j, it's a query made up of clauses. The results of one clause can be used as the input for a next clause in the query. This is a basic query where you basically say match some pattern, and then you can say with some specification where there's specify the condition of the data to be retrieved, and then return, which is essentially your projection of what it is you want to get back out, ordering it in a certain fashion by the order by, and limiting to the number of records that you want, or nodes or edges, depending on what you're querying for, to retrieve. And so on. So you can create nodes with the create relationships similarly, but you have to search kind of for the nodes first, and then you do you can remove both nodes or relations. You can set properties after the fact, and you can remove properties or labels after the fact as well. Here's an example query in Cypher. Very cool language to work with. A little weird when you first start out, but very compelling over time. There's an enterprise edition versus a community edition. The enterprise edition supports caching, clustering of data, and locking. That's what you're going to use if you're going to be running this thing with any size. The community edition's pretty much for educational purposes or for small users. The graph visualization interface, subsets of nodes and edges in the database can be displayed graphically. It uses to visualize query results, and it also can update and drag around depending upon, so you can do essentially data exploration in a simple way. Does support master-slave replication. There is caching and logical logs. In summary, we've talked a lot about NoSQL systems, focusing primarily on storage of big data. General categories that we've talked about include document databases, key value stores, column databases, graph databases, and some of the approaches that span across multiple categories. We talked a bit about consistency, and we discussed the CAP theorem. And with that, if you have any questions, do let me know. That's what I'm here for. Stay safe, and we will speak again in the future.